Today our topic is stress strain diagram. So before we go for the stress and strain diagram, first let's focus about a few definition. What do you mean by stress? So we know the stress is a force per unit area of a material. Okay, so stress is defined by sigma equals to force per unit area equals to, so what is the unit for force is Newton, and what is the unit for area is meter square. So what is the unit for sigma? Sigma, that means stress, is Newton per meter square. Now what do you mean by strain? Strain is, we know, it's a ratio between the change in length by the original length. That is change in length by the original length. That is the length of a material. So imagine there is a bar. Both the side it causes an tensile force P or F. It can be written either of that. Tensile force. So the original length is L. So when it is getting extended, so there is some change in length. So this change in length by the original length gives the meaning of strain, which have no units. Now we focus what do you mean by Hooke's law. Hooke's law is when the stress is directly proportional to the strain. And after that, it is very important thing, within the elastic limit. This within the elastic limit, what do you mean by elastic limit? Suppose, see the same figure, a load is applied, a tensile load is applied on this bar. There is a bar, a tensile load is applied. After I release a load, what happens? When this bar of a material has a capability to restore back to its original position. When it has a capability to restore back its original position, that is a property of elasticity. So as we keep on giving the force on both the side extending, there will be some change in length, and after we release a load, if the material doesn't has a capacity to come back to its original position or original length or dimension, that means it has got some called as deformation. But when it has capability to restore or regain back to its original position or dimension, that is a form of within the elastic limit, that is having an elastic nature. So when the stress is directly proportional to the strain within the elastic limit, this says the Hooke's law. So we have a proportional. To remove the proportionality, we give some constant term, that E. So E can be written as E equals to sigma by epsilon, that is a strain. So what is sigma? Force by area, and what is epsilon? Del L by L, that is change in length by original length. Okay, so if you see there, here we don't have unit, this is Newton per meter square, and here no unit. Okay, so what is the final of this E? Unit of E is Newton per meter square. So this is called as, this constant is called as Young's modulus. So what is Young's modulus? Is an ratio between the stress and strain. The unit is Newton per meter square. Now let's focus on another ratio called Poisson's ratio. It denotes by the word, by the letter mu. So mu, it's a ratio between the lateral strain by the longitudinal strain. So what do you mean by lateral strain? When see this figure again, this considers a circular cross section of a diameter d. So when there is an elongation in this, when the load is applied, there is some elongation, and when there is elongation, the diameter gradually decreases. So what is a change in diameter when there is elongation? That is a lateral strain. So lateral strain by longitudinal strain. So what do we write there? The change in diameter by diameter, original diameter, by the change in length by original length. So it can be also written as a 1 by m. Here also this ratio doesn't have any unit. Focus view of this formula, this is a combination of all the three modulus. E means a Young's modulus, G means a rigidity modulus, and the K means a bulk modulus. So the first one, the first equation says that it is a ratio, it is a relation between the Young's modulus and the rigidity modulus. So you have to remember this E equals to twice of G into 1 plus mu. Whereas in the second formula, what it says that E equals, this is a relation between the Young's modulus and the bulk modulus, that is a K. It is E equals to 3 times of K, open the bracket, 1 minus 2 mu. 2 mu, here minus 2 mu. Okay, and mu can also be written as equals to 1 by m. So this is also you can write in terms of that. And the third one is a combination of all the three modulus, that is the Young's modulus, bulk modulus, and the rigidity modulus. You remember when we are school we used to say we are in kg or something. Remember the kg or a unit of a mass, you remember, that is 9 kg by 3k plus g. It's very easy to remember this formula. It's nothing hard. You remember the word kg. Okay, so when you write this E equals to, everywhere we are writing in terms of E. So here also E equals to that 9 kg, you remember 9 kg, and 3 square is 9, so 3k plus g. Okay, so this is a way you can remember this formula easily. Stress strain curve. So in our y-axis we have our stress, and in our x-axis we have our strain. So this is a curve. We have some five important points. First one is the elastic limit, yield point, ultimate limit, and the breaking point. The 4 points are there. And after that we have the strain hardening. So what do you mean by strain hardening? The lower yield point to that ultimate limit, that the region between those fees is called as a strain hardening. What happens there, for ductile material it gives how much strain by plastic deformation. It shows this property. And what do you mean by necking? Necking is that from the point from the ultimate limit to the breaking point, the region between those, it gives an necking point, or necking region rather we call it, say. And what do you mean by elastomeric? Elastomeric we say as per the Hooke's law that when until the stress is directly proportional to the strain, okay, within the elastic limit, means when the load is applied to a body or a system or a material, when we release the load and when it has a capability to come back to its original position, okay, so that is the limit. This is, or we called as a limit of proportionality, this point, or we can say as 0 to A, then B, C, D, E. Let's name that. So the 0 to A point is called as a elastic limit or limit of proportionality. As we keep on giving load on a structure or a material, after this limit what happens? It increases some amount of stress with respect to strain. But when we release that load, it doesn't come back to its original position, but it comes somewhat regain but doesn't completely come back to its original position. So as we increase in giving strain, that is change in length with respect to original length, what happens? There is a yield point. Okay, after that if we keep on increase the load, what happens? What we can see, there is a curve called, see the CDE, you can see the curve, and the D point you see we gives an maximum yield stress, we call as maximum yield stress. What do you mean by maximum yield stress? At the point where the maximum stress occur. This can only happen only for the ductile material, only for the ductile material. This kind of maximum yield stress or the ultimate limit occurs only for the ductile material. So as we give the load on the structure, what happens? This region keep on thinning it, and there will be keep on increase in, there is a keep on increase in the material structure. Okay, okay, and after that, after this region, the D point, when we keep on in giving load on the system or a material, what happens? This region, no, forms a necking, like our neck. Okay, so keep on necking, and some point what happens, it get ruptures, or we can call as breaking by increasing load. That is called as a breaking point, at the point where the after inputting giving load the material fractures or break. That is called as a breaking point. And from this point A to E, the total nature is known as a plastic behavior or plastic deformation behavior. Two of the patterns, that is how it looks for brittle material. If it is a brittle material, you see when it is drawn with the stress versus strain, the line can see it's a correctly linear curve. It's a straight line. Okay, the example of brittle material is a glass, then what you can chalk, and etc. These are the properties of a brittle material. Now let's go for a copper. If there is a copper, how it looks like? There is no buckling, much buckling, like there is no point of yield stress and maximum. Directly it creates a maximum and it ruptures here. It ruptures here. There is a property of a copper material. Now let's see some comparison of various curves. So here we have four curves, that is A, B, C, D. So each curve says its each properties of or characteristics of the curve. The curve A says that the strongest and the stiffness have the maximum strongness. This case a maximum strongness and the stiffness, and curve B represents it's a most brittle. Why? Because it's directly ruptures here. Curve C says it's a mostly ductile in nature, and this D says that since the properties which it ruptures before this thing, so it it's a ductile, it's also a ductile material but material whose stress is low, or we can say whose stress is low. Okay, so how, if the question comes in that way, like they have given this kind of curves, and how you can predict the which one have the maximum slope. See, the strong and the stiffness, the material causes like have a maximum slope. Then the brittle, you see the brittle, you can find out like there won't be any buckling form or no curves. Okay, it's a directly a linear straight line. So those kind of curve is mostly a brittle, like glass, chalk, etc, etc. And then this one you curve that previously I have shown some copper or aluminium kind of soft material, or this can be other, if there is a comparison between C and D, this can be a mild steel. This can be a mild steel too. And if there is a comparison, then obviously the low stress causes by the aluminium. This can be an option like that. So you accordingly have to choose the right option in the point of exam. Here another few different buckles of curves are shown. There is another A, B, C, D. See here, compared to previous one, see here, This A1 shows a property as a milestone, and the B1, you see what is the difference between A and B. The yield point are very low, and that ultimate point is also very narrow. So when there is a comparison between these two, so obviously you make sure that the curve A is an ductile material, and make sure this is an mild steel. Okay, and the curve B is for aluminum or copper. Now see the curve C, you see that directly it comes and breaks here. So obviously it is an brittle material like glass, chalk, etc. Yeah, and see the curve D, it is going a reverse parabolic form. Reverse parabolic, it is the curve is going towards upward direction. Okay, this is the property for the elastomers, or what we call as the elastic material. Okay, like rubber. This is an example.